Bare skru på den nå, du. Ja, så da kommer den. Det må ikke være her.
Nei. Skal jeg gjøre det? Fingertingen?
Ja, det sånn det blinking når jeg gjorde det, men det kom ikke på.
Ja, jeg måtte bare halvtrykk skjøtter. Okay.
Ja, riktig. Nei, men da vi i gang. Ja, den skjøtter jeg.
Ja, da vi i gang. Okay. Have we all returned to the room? Okay, some solid 1955 memes going on here. This originally showed up in an IBM mainframe room in 1955, actually. So I like it. Got to have some programming humor. But first, before we continue with blinking lights, I want to see if I can... and does it actually pause? Yes, it does pause. Do you all see this? Okay. Who here has taken this course? Okay. Who here has not taken this course? Because it seems like it's most of you have in fact taken it. Okay. So I'm just going to briefly explain the last exercise in this course. The last exercise here, in that course, which is colloquially called Byggeren, or the builder, you put together a bunch of computer components to create a computer system, and this computer system is supposed to let you play a game of Pong against, well, yourself for the most part. So the green board there on the right-hand side, lower right-hand side of the picture, contains a motor on the left-hand side of the board, which controls a bouncer type thing that lets you push a ball upwards a hill and it will roll back down towards you. And there's also a servo motor on that one so that you can control the angle in which you bounce the ball. And of course a solenoid that lets you actually actuate the pusher that pushes the ball. And all of this is controlled from a different microcontroller, which is the little white one, which is similar to the one I had on the document camera down here. This one contains a joystick and some capacitive touch sliders. And you're supposed to use these to control the motor and the solenoid and the servo. The challenge is, of course, that those things live on one microcontroller, and the things that control the motor output and the servo output live on a different microcontroller because of reasons. And these are connected together with a data bus. I'm not going to go into the details of the data bus, we just need to know that there is a data bus. So we have two CPUs that are doing different things, and they are connected together with a message channel. Okay, so the final exercise is read the joystick positions and the sliders, send this information over the network, or, well, over the network essentially, to this other processor. This processor reads this message and decomposes it, and also controls this motor, and this motor should have a PID position controller, so it needs to be running somewhat periodically. And then there's also a servo that needs to be controlled, and of course a solenoid. And there's also an IR sensor that detects if the ball goes past this pusher so that the game is over, or to detect that the game is over. And you should also have a counter that counts the number of seconds passed or something like this to give you some kind of score. Okay, so let's list up all the things I just said. So we had read the position sensors on one thing, send them over the network, decompose them, and also do periodic PID control, and also periodically have a counter, and also detect the IR sensor and send that message back over the network. So there's at least 5 different things going on. And these people haven't learned anything about threads yet. So the question is, how does anyone want to present how they solved this conundrum? Or rather, let's put it a different way. Who here actually managed to solve that conundrum? Well, there's a smaller amount of hands than the people who took the course. So of the 5 people who did, in fact, sheepishly put their hands up, it's like, yeah, we did kind of solve that. How did you solve it? Yes?
With flags.
We what?
With flags.
With flags. That's a little vague.
Timer interrupts.
Timer interrupts? Okay, timer interrupts is a good solution because timer interrupts are running concurrently with the other things. When an interrupt triggers, let's do some very basic hardware stuff. When an interrupt triggers, what it does is it yoinks the thing that controls which part of your program is running, just grabs that and moves it to another part of your program and runs that instead and then moves it back as if nothing has happened, except some time has passed. So what you're doing is effectively you're threading. Good solution. Well, there is in fact a non-interrupt based, non-threaded solution. I'm going to go through that one right now, just to show you how hairy it is. And I'm not going to code it. I'm just going to talk about it. Okay, so polling the joystick and the sliders. This is polling, so this is done periodically, which means that the message is being sent over the network is also happening periodically. Every time you receive a message, there should be some amount of period that has passed, and it should be relatively constant, and hopefully is entirely constant. You can use that period to perform the PID control, because that needs some periodic execution. So now you get the period over the network, and they are controlled together. Then after you have received a message, you read the IR sensor and send something back if there is something there, and you also increment the counter. So you're using the period of one thing as the period of the other things. It's not a nice solution because if you need different periods, of course, everything breaks down, but it is possible. So who here who took that course think they would have had an easier time if they did actually have an operating system and can separate this into threads? A couple of hands. So what I wanted to show you here, just briefly, was that you can and should think more about how you can separate programs into threads. Try to, when you have a problem, try to see if you can decompose it into reasonably independent things. But there, of course, there is a challenge, and that challenge is that sometimes you need to share information. For example, when you receive that message controlling or containing the joystick positions and so on, if that was one thread, if there was one thread for receiving messages and then there was another thread for controlling the motor periodically with a PID control, there's some need for information flow from one of these to the other. And the question is, how do you do information flow? Well, okay, we have 2 people. How do you do information flow between 2 people?
Dialogue. A dialogue.
A dialogue. Yes? Dialogue technically means conversation between many. So I guess it would be more appropriate to say duologue. But I digress. But in fact, well, we're computers now, so I guess even more technically correct, it would be 2 monologues. Perhaps. Might be even easier. Okay, but the problem is sharing. At some point, we do in fact need to share information between our threads. And we did see this to some extent with this UART resource. The UART resource was shared, but there wasn't, well, the resource is a kind of information, but there's no flow of information from one thing to the other thing. So we're going to talk about how to identify that flow, or first you identify what the threads are, then you identify what the flow of information between threads are, and then you go, how do we solve this? So we're going to have to look at these resource mechanics and how they actually work. Does this mouse have like a USB thing that let me plug it into the other? No, it doesn't. It's connected there. Okay. So is everybody familiar with this piece of code? Does anyone have any issues with this piece of code? Any pure functional programmers in the house? Okay, no. Good. Well, I mean, you're allowed to be here if you are a pure functional programmer, of course, but okay, so can someone explain what's going on here? This should be pretty elementary programming, and if you can't explain this, I would be slightly disappointed. So you're not allowed to answer because you're already getting an A in this course. I want somebody who's getting an E. Okay, you're not getting an E because I say so, but... Okay, well...
So it's fetching the value of I first, and then incrementing it, and then assigning it to I.
Okay, so fetching the value of I first, then incrementing it, and then assigning it to I. Okay, 3 operations. Did you read my slides? Okay. Now, what we did in our operating system was we invented a mechanic, and I'm not going to go into the excruciating details on how this mechanic works, but I can if you're interested. What we did is we implemented a mechanic that let us interrupt execution of code at any time, or specifically at every millisecond precisely, which means that we can interrupt the execution of this piece of code at any time. We can interrupt it before reading. Well, that's not a big deal. We can interrupt it between reading and modifying, or between modifying and writing, or after modifying, because these are 3 independent actions. So, since we can be interrupted at any time, what happens if we have 2 threads that are doing this piece of code at the same time? Okay, can I have 2 volunteer threads, please? I need 2 volunteer threads that can add 2 numbers for me. And one of the numbers is going to be 1. Okay, well, let's just pick you 2. I'm going to give you both a number. I'm going to give you the same number, and I want you to increment it by 1, and I want you to tell me what the answer is, okay? Are you ready? Okay, the number is 5.
6.
Okay, so then 5 plus 1 is 6. It's hereby confirmed mathematically that 5 plus 1 is in fact 6. Well, that's what they said. I gave 2 people the job of incrementing by 1, and they reported that the answer was 6. So what's the problem? Okay, one of you is a bit slow. You're on the slow end. Okay, so I'm gonna do the same thing again, and you need to listen to all the numbers that do in fact exist, not just my numbers. You ready for this challenge? Yes. Okay. So I'm going to give you the same number again. 5.
6, 7.
Look. Oh, suddenly 5 plus 6 plus 5 plus 1 is in fact 7 this time. Well, that's confusing. So we shared a number and we got some different results even though we did the same thing, because the same thing wasn't done in the same order at the same time. Whew, that's a mouthful. So we enter this situation where the work of one thing can be overwritten by the work of another thing because they are interrupted at different times. So let's see if we can precisely identify what the problem is. Using a resource simultaneously, well, we experienced this with the UART thing. We also found out that there is a problem where the result depends on the ordering in time. If we had one thing that responded a bit later than the other, then we got a different result. Here's some terms for you to write down. The blue words are terms. This is known as a race condition. A race condition is when the result depends on the ordering in time. And you may actually have encountered this before in a circuit course. Did you encounter this in like the SR switch type stuff, where if you input a 1 volt, go from 0 volts to 1 volt on the same thing, then the result on the end actually depends on the travel time of the electrons. Did you encounter this one? No? Okay, it's probably too complicated. Whatever. But race conditions exist in more than just computers. It's not necessarily a completely computer word, even though it's mostly used here. So, the result depends on the ordering in time. So what's the solution to this problem?
Slow everything down.
Slow everything down. Well, if you slow everything down, there's still an ordering in time that it depends on. It's just an ordering in slow time. So it's not quite the solution, but we're approaching a solution. Speed everything up. No. Okay, next.
Make certain operations not interruptible.
Make certain operations not interruptible. Yes, you are doing the thing where you're skipping over one thing. But yes, if you're making things not interruptible, what have you actually achieved in regards to ordering in time? If it can't be interrupted, you've guaranteed some specific ordering in time. Because one thing must complete before another thing can start, hence an ordering. So, two solutions. Prevent things from happening at the same time, so that they must happen sequentially. So what we're doing is, instead of things happening at the same time in parallel, we're forcing things into some kind of bottleneck where only one thing can pass at one time. What's the problem with doing this? Well, I've used kind of the incorrect term here, but I think it might be technically correct. It definitely removes parallelism, because now things aren't running at the same time. But it also, to some extent, removes concurrency, because even though you can't interleave them anymore because you've decided that the interleaving was a bad idea. That's one solution. There's also another solution, which is kind of a YOLO, is this really a solution? Can anyone guess what this could be? I'm just going to spoilers. Don't share resources. Well, if you're not sharing anything, it doesn't matter if it's interleaved. The problem was sharing, so don't share. Of course, that's not always achievable, but there is a different way of thinking about this kind of problem. So instead of sharing the data, what you're actually doing is you're communicating the data. We're going to cover the difference between sharing and message passing in more detail. Well, we're going to cover it in more detail today, I guess. So, yes.
When you talk about resources, do you always mean like hardware resources?
When I'm talking about resources, do I always mean hardware resources? No, they don't need to be hardware resources. Like the number, the I equals I plus 1 number isn't a hardware resource in that sense. I guess you could call it a hardware resource because it is a number that is stored in memory, and memory is hardware. So in that sense, it's hardware. But in another sense, it doesn't need to be hardware related. But I guess now the question is there any kind of resource that isn't memory or hardware, under which memory is in fact hardware? No, that's actually a good observation. Do you have any pure software, non-physical memory location type resource?
So access to a library, where the access it starts to get abstract, and I have this feeling that we can find further abstractions that are where the hardware aspect is lost. That still needs to be shared. But well, if you really start drilling, you will end up in some memory, possibly.
Yeah, I don't think there's a way to store memory without memory. So, do you need a resource to protect a non-physical entity? Oh boy. Oh boy. Let's not go any unnecessarily deep on this one. I mean, I think we can, but not today. I need to think long and hard about to give you a good answer to that one, I think. So for now, the answer is no, I think. Or is it yes? I can't remember exactly how the question was worded. Okay, so let's look at the first one, which is introducing bottlenecks. So let's discuss messages and direct communication at some slightly later point, which means like 10 minutes. Okay. So this is what we did in the UART resource. We had some kind of flaggy type stuff that says that this thing is currently occupied and you are not allowed to enter. Of course, the flag is memory, and the flag is probably some kind of integer. I mean, everything eventually becomes ones and zeros. And so modifying a 0 to a 1 or a 1 to a 0 is, of course, a read, modify, write type of operation. And what we need is a read, modify, write operation that cannot be interrupted. Because if it can be interrupted, we're back to using flags to protect the flags, and now we have a recursion flag loop, and that doesn't work. So we need to make sure that the modification of the flag does itself not introduce a race condition, which means that flag modifications must be completely indivisible or uninterruptible. And this is known as an atomic operation. Atomic from Old Greek, you're probably familiar with the word atom. Indivisible. Of course, the atom turned out to be divisible, but let's disregard that for the time being. And as it turns out, most atomic operations on modern hardware are in fact also divisible. So let's ignore that for the time being. x86 is a scary place. Don't ever go there. This is the scary place in gray text, so don't worry too much about the gray parts. But if you do want to go into scary places, look into things like the lock prefix and M fences and stuff like that. And of course, the compare and exchange pseudo instruction, it is of course not a single instruction on x86 because x86 processors are running microcode, and microcode is like firmware for your CPU, which is scary. So exactly how this works on a hardware level is not part of this course, unless you've recently added it. No. Okay, good. So the point is that at some point you will actually need hardware mechanisms here. You can't avoid this. You need hardware that supports some kind of atomic operations, because otherwise you cannot implement an operating system for it. There's just no way around that. So let's discuss the most common kind of bottlenecking type stuffs. The first one is the semaphore. Semaphores are an old French invention. They're literally flags, and they're flags used for signaling messages over distances. And this, in this case, in computer language, this is an integer flag, and this flag has a value that is always greater than 0. This lets us do some interesting things. Also, by the way, notice that these things are atomic, so this is an atomic integer. If you increment it, incrementing it is a single indivisible operation. So we have two operations for this one. Of course, it's an integer, it's increment and decrement. And these have been given Dutch names from Dijkstra. I think that's how you pronounce his name. So these often have the Dutch names in the literature, but often also just the weight and the signal, or the increment and decrement, or if you're in Linux source code, they're just called up and down. So in the UART resource situation, we had a resource which had the value 1, which means that we can decrement it once. Once it has been decremented once, it now has the value 0 and cannot be decremented further. Anyone that tries to decrement it will now stop executing until the integer flag has been incremented again by someone else. You cannot increment the flag yourself because you are stopped from executing. So the key here is that if you are blocked from executing because you want a resource that is not currently available, you need to wait for someone else to make it available. So the semaphore lets you communicate resource availability from one thread to another thread. And by communicating resource availability, well, you're denying access to the resource from someone else, hence introducing a bottleneck that prevents concurrent execution. Everyone with me so far? Anyone like completely fall off? You're still like barely holding on? Okay, good. Of course, what would have happened if we started that value at 2 instead of 1? Well, then two things could increment it, or decrement it, sorry. Two things could decrement it, and now two things are using the resource at the same time. And that's not necessarily all that useful. Sometimes it's useful. For example, if you're asking for the number of things available in this memory location, for example, the number of messages in a queue, for example, then there could be more than one message. And so if you can decrement the semaphore, there is a message there and everything is fine. If you can't decrement the semaphore anymore, there is no message there and you're not accessing invalid memory, for example. But in this case, we want just the binary semaphore. We just want the semaphore that can be either 0 or 1. But there's still one more problem with this. The problem is that somebody else can just kind of show up and they've never used the resource and they're like, by the way, I've unlocked the resource for you. And that's not cool. You don't want somebody else unlocking the toilet door while you're inside. You want to have the sole ownership of your private space. So what you do is you want the binary semaphore with ownership. And once you have included the ownership semantics, now you have exclusive access over it, and you have anyone who uses it has exclusive access, and so hence you are mutually exclusively accessing this resource. The mutex is definitely the most common resource sharing mechanism, and in my toy operating system, resource is a variant of mutex. This is not precisely a mutex, I'm not going to go into the details, but it behaves most similar to a mutex. You can only one thing can use the resource at a time. You cannot have multiple users over the resource. Mutexes also allow a bunch of other things that we're going to cover later in this course, when threads are in different amounts of importance. So you want to make sure that you're always running one thing first. If two things are runnable, you always want to make sure that you run one of them because it's more important. And if you're sharing resources, some weird stuff happens there where you can't run the most important thing because it's using a resource that's shared with something that's less important, and now you're in a conundrum. So it supports things like priority inheritance. It also supports something that I haven't mentioned, and it's mostly because it seems very obvious, but it might not be. You can lock multiple mutexes at the same time. So if you have different resources that you need access to, you can first take one resource and then take another resource. My operating system does not allow that. You can only have one resource at a time. Okay. So let's think more precisely about exactly how you use them. Because once you have these locks, these locking mechanisms, you can take it often, take it only exactly when you need it, and then try to release it as much as possible so you're not hogging the resource. Or you can take it for a while and say that I'm going to need this for a while now. I'm not using it right now, but I may need it later, so I'm just going to keep a hold of it. And there are valid reasons for doing both of these, but for the most part, people tend towards the fine-grained locking so that the resource is as available as possible for everyone else. The problem is when you start using multiple resources at the same time and you let everything be available and somebody else takes one and you need both, and kind of weird stuff starts happening there. So we will explore semaphores and mutexes in further detail. You will explore semaphores and mutexes in further detail, and specifically the challenges that occurs when you're working with more of them at the same time, and how they compose, and the code quality concerns that happen when you start using it. So this is exercise 2. We're going to do the I = I + 1 simple thing. We're going to run it on Linux. We're going to see that it doesn't work as expected, which is expected, so therefore it does work as expected, I guess. And then we're going to use a mutex around it, and we're going to see that, hey, now it's actually legitimately does work. It's just to get you started with some basic programming and basic threads and just kind of get it into your fingers. Then the second thing we're doing in that exercise is we're going to do message passing, and we're going to use Go for message passing. And Go is Google's programming language because Google decided that we have Google-sized problems, so we need a Google-sized programming language. So since they have very large problems, they decided to make a very small programming language. No, seriously. Because if you have a large problem, you have large amounts of people working on the problem, and you want to make sure that the people are solving things in the same way. And so you want to limit their options to the correct way, whatever you decide the correct way is. And so that's what they did. So Go is a C clone for the most part, with a couple of valuable things like arrays, proper arrays, garbage collection, so you don't need to malloc and free yourself, and message passing, basically. So very useful language, but of course it's missing a couple of things that would be useful, like for example templates. But how many here have actually used templates properly? One person. So, I mean, that's disappointed. You took a C++ course. Who took that C++ course, by the way? Okay, and none of you have used templates properly? Oh, come on. I was like, at least you know what the STL is, right? Did you use like an std vector? And so somehow you managed to use an std vector without using templates. I'm impressed. So you have used templates. Okay. The point is, it's a data structure that is type dependent. Or you can have a function which is data structure dependent. So a sort function, well, sort what? Sorting strings and sorting integers is quite a different operation. So you need a templating operation. And Go does not have this. It has sort.strings and has sort.int. So you have different functions for sorting because of this. So if you want to sort your custom data structure, pain in the ass, but it's doable. Same way as in C. So the two approaches to solving problems here are fundamentally different. The I = I+1 problem isn't solvable with message passing in that sense, because it requires sharing the I variable, and you can't share the I variable. So what you instead do is you have the I resource is in fact a thread. The thread is the resource. The thread contains internal state, which is the resource. And then you send it messages which are of the kind, hey, can you increment the resource for me? Or, hey, can you decrement the resource for me? Or, hey, can I get the current value of the resource? And then it will reply back, here's the current value of the resource. And what you've achieved then is effectively serialization. These are not happening at the same time because you can only read one message at a time and therefore only handle one message at a time. Thereby you avoid this whole sharing problem. But of course now you have a communication problem. So there are a couple of different ways of doing message passing, and they're done in different ways in different languages. We're not going to go into super high detail here. Go is asynchronous message passing, so that if you send a message, somebody must be on the receiving end, and if there is none on the receiving end, you will wait until they show up. So if you just call send and there is no receiver, you will hang, essentially. Erlang, on the other hand, is asynchronous. If you send a message, the message is sent, and you just have to, the receiver will hopefully show up at some point in time. And if the receiver doesn't show up, the message is lost forever. And then you have the symmetric versus asymmetric kinds, which is seen not from the sender's perspective, but from the receiver's perspective. Do you know who sent you the message or not? And in order to know who sent you the message, there must be a kind of connection between them, which usually means that there's a channel between two threads. So you create the threads, and then you create the channels, and then you connect the dots together. In the asymmetric case, usually there is no channel. The thread has an inbox. So you're not sending over a channel, you're sending to a thread. So again, in this case, Go is symmetric. You sending over a channel. And in Erlang, it is asymmetric. You're sending to a thread. So I'm going to show you some Go code. This is mostly for your own resource when doing the exercise 2. You don't need to. Does anyone have any like big problems understanding this? It should be it's designed by Rob Pike to be fairly immediately understandable. Let's do some reading and receiving from channels. The arrow operator is the relevant operator in this case. So if you have a channel on the left-hand side and a value on the right-hand side, you're sending to the channel. And if you're doing it the other way around, you're receiving from a channel. So the arrow always points to the left, unfortunately, but that's the way it is. And also the bottom line there is you can receive a message from a channel and not care what the value is and therefore not store it, which is useful for just signaling something has happened, and since you receive the signal, you know that the thing has happened. You don't need to know any further details, for example. Of course, if you're sending over channels and you're not sending two threads, then you need to be able to, well, you would like to be able to listen to messages coming from multiple channels at the same time. For example, the integer resource, you want to have a send or an add event, a subtract event, and a get event, which are three different channels. So there needs to be some mechanism for listening to multiple things at the same time. And that mechanism is called select. And in Erlang it's called receive, I believe. And here you can, it's like a switch case, but for channels instead of values. And this lets you listen, so whichever one happens to happen is the action that you take. And then it immediately, it's not like, there's no fall through here. So this is a zero fall through switch case for channels, I guess would be the simplest way to explain it. So, I am not going to, because of time, I'm not going to tell you exactly why this is the correct way to do things. You're going to have to, I want you to think about why this is the correct way to do things. Let's put it that way. For some time later. Food for thought. Brain juice. Why is it correct to do it this way? Okay. You have a bunch of things that can happen. A bunch of things you are communicating with, they can decide to communicate with you at any time. Therefore, anything that is concerning you can happen at any time from any place. Therefore, you want to have a bunch of things that you are listening to with a select case, and then consider them simultaneously, and then perform whatever action was requested of you. So things are request-oriented. You ask for someone else to do something for you, and then they will do it, and they may in turn ask someone else to do something for them. So the thing I want you to think about is, why is it correct to organize your program in such a way that everything is waiting for stuff that is requested of them? A passive system. Why is this the correct approach? We also, just to conclude the message passing difference, there's no need for mutual exclusion here. Okay, spoilers, this is one of the reasons. There's no need for mutual exclusion here because there's nothing that is shared. Because if things are requested of you, it means that there's something that you are solely responsible for. And if you're solely responsible for it, you are not sharing it. So the way we think about it is these things are passive actors in a system. And you are the other threads, they're kind of directors for each other, I guess. And of course, these actors are free, basically. They don't really cost anything, so you can make as many as you find necessary. So this is another way to solve the same kind of problem. So this, if you're doing, I guess if you're doing toilets with message passing, is going to be quite different because there's no shared lock. There's no door lock isn't a resource. Instead, there's a janitor that is responsible for locking the door for you. And the janitor never needs to go to the toilet, so that's fine. So you request someone to open the door for you, and if somebody else requests the door to be open, they say, no, I can't do that. So the thread is the resource in this way of thinking. What's the next slide? I don't remember what the next slide is. I've already said this, so you can just read it. So this is the correct way to create a message passing program. I'm just going to say this now, and we're going to keep saying this later until it kind of is smashed into your brain. We already know that this is the correct way to do it, and you don't really need to argue with me on this one. To put it this way, if you decide to write in a message passing language, and you at some point say, you know what, I think I'm going to use a mutex here, the answer is no. You're doing it wrong. Because you can organize any program. I am claiming this, you can organize any program in a message passing way with no shared resources in an efficient and elegant way. That is my claim. And if you are deciding to use a message passing language, which you will find more intuitive than a shared variable approach, is also a claim that I'm making. There are a couple of, okay, there is one way of solving the elevator project, which is more shared variable-y, which is quite nice, but is also quite difficult to do. But all the other ones tend to end up being most elegantly expressed with message passing, turns out. And if you are going to do this, I want you to think about why exactly is this the correct way to do it. It's kind of the same thing of thinking about state machines. Why is it the correct way to have the events on the outside and then the states on the inside instead of switch state then switch event? Why is that the correct way when you can do it both ways? Same kind of, in the same ballpark kind of question here. Why is it the correct thing to switch on the requested event first? Why should every thread be a while loop with a select inside it? I want you to think about that. Final slides are just exercise 2 relevant stuff. I'm not going to talk about them because time. There's this, if you do send a message containing a pointer, now you have 2 threads that have access to the same memory location. It's kind of a technical thing going on. This is impossible to do improperly in some languages like Rust and D, and is definitely possible to do improperly in languages like Go. So it's kind of a beware. This is guaranteed to happen to some Go programmers, and they're going to tear their head out wondering what's going on. And the final slide is just some weird code that you can copy paste. Because if you have something that you want to send out from one thread and duplicate it such that it is sent out to, the same message is sent to 2 threads. So you have a 1 in and 2 out or multiple out channel. You're going to have to start messing with duplicators and repeaters and so on. So I created a simple little doodad that takes one message in and duplicates it to send to multiple people. You won't need this for exercise 2, but you might need it for the projects. I'm just including it here. So that's the end of slides, and it looks like it's the end of time as well, unfortunately. So if anyone has any questions, we'll just take them down here afterwards. Yeah.
Ja, vi copycat.